In this problem, we're looking for the intervals of concavity and the inflection points. Well, both of those require finding the second derivative, so that's where we're going to start here. I'm going to find my first derivative so that I can then find the derivative of that, so that I then have a formula for the second derivative. Now, the very first thing I would need to find with this one is the points of inflection, because the points of inflection are what separates the intervals of concavity. So my inflection points here are going to be where the second derivative equals 0. So I set that equation equal to 0 and solve from there. And when we do so, we end up with x squared equals 1/3, which means I then take the square root of both sides. And when doing the square root of 1/3, there's a couple things that are worth remembering. Now, first of all, if you want to write it as just 1 over the square root of 3, that's fine. I'd rather not see square root of 1 over the square root of 3, though, because the square root of 1, of course, is just 1. So 1 over root 3 would be good there. Technically speaking, though, if we wanted to actually rationalize our denominator, then you would actually end up having root 3 over 3. It's even better. But I'm guessing most of you will probably write it as 1 over root 3, so I'm going to stick with that for the moment. But there's one other thing we need to remember in this process. We are doing x squared equals 1/3, so we had to take the square root of both sides. When you take the square root of both sides, remember the plus or minus. This actually has two solutions. It has a positive 1 over root 3 and a negative 1 over root 3 as possible solutions. So there's actually 2 points of inflection in this problem. All right, so now I'm going to set up my intervals of concavity. So my intervals, they start at negative infinity, and then they go up to the leftmost of my solutions. Now there are 2 solutions here, 2 points of inflection. And so the leftmost one is going to be the negative 1 over root 3. Then I go from the negative 1 over root 3 up to the next one, which is going to be the positive 1 over root 3. And then from there, we can go from the 1 over root 3, the positive one, up to a positive infinity. Those are our 3 intervals of concavity. The only question is, for each of those 3 intervals, is it concave up or concave down? And to know that, we're going to test some numbers. For this first interval, I see that -1 looks like a nice easy number, so I'm going to check that. Now, in order to check it, I'm going to be plugging it into the second derivative. I want to know whether it's concave up or concave down. The second derivative is what tells us about concavity, so that's why I'm plugging it into the second derivative there. So I plug the -1 into that equation, and I get -8. Therefore, the second derivative is negative, therefore it is concave down. All right, next one. I need to check what's going on with this interval, and a nice easy number to check within that interval looks like it would be 0, so I'm going to do f double prime of 0 for that one, which gives me 4. Notice it's positive, therefore, throughout that interval, it is concave up. And finally, for this last interval, I'm going to be plugging a positive 1 into my second derivative function. Again, you don't have to use 1 or any of the other numbers I'm choosing. I'm just choosing something that I think is pretty easy within that interval, but there's lots of other numbers within this interval that you could have chosen. But if I use 1 and plug that in, I end up getting -8, which is a negative number. Therefore, since the second derivative is negative, our graph is concave down.